next speaker, that is Graziella Lorit from Microelectronics Research Unit, University of Oulu, Finland, and we'll talk on carbon nanotubes boost cell alignment.
Thank you. Thank you for the committee to accept my work to present here. It's the first time I'm here and I have been enjoying and making new connections. I'm going to talk about carbon nanotubes to align cells. So I don't know how many of you are familiar with carbon nanotubes, but they have been used already in commercial sport equipments and also in electronic devices. They have very good properties in several ways, but I would like to emphasize the ones that can be good when we are talking about cell control. So first, carbon nanotubes can offer you nanoscale diameter and microscale length. And in particular, in the nanoscale, they can mimic protein size. So the cells can kind of like to attach to them. You have a very freedom of synthesis, so you can do them as powder dispersion templates and create three-dimensional matrices too. They are very easy to functionalize. So also for applications like biosensors, they are very good. They have outstanding electrical conductivity, and also they are very strong materials. The mechanical properties are very good. That's one reason they have been using in sport materials, because they reinforce structures and make the material stronger. In this work, we have been creating templates by using lift-off procedures. So basically, you get a substrate, you do some mask that you can create the partner you want. And after that, use catalyst chemical vapor deposition to grow the carbon nanotubes on the templates. As a result, you have these pillars that come out from the surface. Our first test, we did a design that there was 4 different structures. The first one, we have smaller pillars. They were 5 by 5 microns and 10 microns tall. Then we have the other 3 with 20 by 20 microns, and we changed the distance between them. Because of a matter of time, I didn't show the results for the cell growth in those templates, but the main result is that when we grow the cells in the 5 by 5 microns pillars with a distance of 10 microns between them, we are able to orient the cells. The other templates, the pillars are just too far away, so the cells just behave like in a flat surface between the pillars. Based on this first result, we also create, using these 5 by 5 microns and the 10 microns distance, different kind of templates. One as stripes, so we have 3 lines of these pillars with these dimensions, and we separate those lines for 25, 50, 100, and 200 microns. And we also created this kind of spirals by having the same distance of the pillar. And that's where the interesting results come. Before I go to the results, which applications we are aiming for by using these templates, we have been applying them in 2 different cell lines. One for neural cells. The importance of aligning neural cells is basically related to spinal cord injuries. And in the chondrocytes, our main cells in the cartilage tissue, you want to find different orientations when you are talking about tissue engineering. So that's the motivation of these templates. In parallel to the carbon nanotube templates, we have created also some silicon oxide pillars by using etching. And the reason is, it's very well known in the literature that if you change the topography of your substrate or your scaffold, you can manipulate how the cells grow. So we want to be sure that whatever we are seeing is because of the carbon nanotubes and not because of the topography that the pillars create in the microscale. And here it comes the first results with the neural cells. So when we have carbon nanotubes, we could see this network created by the neural cells. So we could find some neural cells and start to follow, and they just grow these axons all along, connecting pillar to pillar. When we go for the silicon surface, then we have these very large bundles. So they don't do this kind of thin connections between the pillars, but they just have these very thick bundles of actions connecting the pillars. The other interesting point is, well, in the silica pillar where you don't have the nano structure, the cells go through the attachment just by wrapping the pillar as a whole. But when you have the carbon nanotubes, you can see these interactions on the same nanoscale between the cell component and the carbon nanotubes. Here we have this array, but then when we arrange those pillars in stripes, then we could see, this is a live dead image cell, fluorescence image. So you can see that the connections between the pillars just follow the straight line. Of course, you have some clusters of the neural network, but you do have the alignment. And as the cells between the pillars, as you see, don't really like it, so they were mostly dead. So cells seems to like where the carbon nanotubes are. And here we have electron microscope image, and you can again see is in particular this area here. So you can see the connection of the pillars by the cells. So we are able to make this unidirectional alignment of neural cells, and not just in stripes, but in any geometry. So when you go for the spirals, then you can see that it also makes the connection of the carbon nanotubes. This capability of using them to have this unidirectional alignment is also true for chondrocytes. So here now we have chondrocyte cells. They will grow for 7 days. And when you have the array, you can see that they are either horizontal or vertical grow. When you have the stripes, the cells just follow the stripes, and then when you have the spiral, they follow the spiral. With the chondrocyte cells, we did some further analysis. So what we did is we have marking the nucleus of the cells as ellipse, and defined that the horizontal line in the image is the 0 degrees. And by that, we have measured what was the angle that the cell was. And by doing that, we created this kind of graph that you can see what is the angle that the cells are. As you can see, they are mostly or in 0 or in 90 in this kind of array. When you check the stripes, so here we have the stripes for silicon as reference and the carbon nanotubes. When you do the same kind of analysis, then again you are going to find that they are mostly in 0 or 108 degrees. That means they are following the stripes line. And another important information from here is that if you get the same time point for silicon and carbon nanotubes, you have much more cells on the carbon nanotubes than in the silicon, that's showing that they support better the survival and the proliferation of the cells. In terms of attachment, we observe some very similar thing than the neural cells, that the attachment points of the chondrocytes for silicon, they grab the whole pillar as a row, but when you have carbon nanotubes, they do the interaction in this nanoscale structure. So why we want to use the carbon nanotubes with the cells? So as I mentioned before, the nanostructures mimicking the proteins or collagen dimensions, what promotes this adhesion attachment in nanoscale level. The pillars are flexible, so it gives a mechanical environment that is different of rigid pillars. And I wouldn't have time to show here, but we have a whole study also using some finite element analysis that we can use these templates to estimate how much force the cells apply in the environment. So that might be a very good application. And what else? They are very conductive, so for neural cells where the signal is based on electrical signal, that might be a very good advantage. They have the capability of absorbing proteins, again easy to functionalize, and as I showed, there is a long support for long-term cell. What we are doing next with these templates, of course, we cannot think in these templates as a scaffold since they are in a hard surface, but it's now ongoing to make a carbon nanotube-based microelectronic arrays to evaluate the electrophysiology of cells. So this is one picture of one of them that we are now developing. We hope that the neurons are going to do these connections and we can measure them not in a flat surface but hanging. As I mentioned, we have some studies that we could use these templates as model to evaluate how much traction force the cells apply. And I also have now national funding that are supporting the alignment of carbon nanotubes inside of hydrogels. So we hope that we can align them in a three-dimensional structure. I would like to use here a bit of open for collaborations. So we are seeking for collaborations, especially if someone here works with scleroderma cells or knows someone that could be interesting. So we could use these templates as modeling, prediction modeling for this kind of disease that the elastic is important. And we are looking for partnerships in this buff of calls that was showed us early. That's all from me for today. This is my team in the University of Oulu. Those are my collaborators in this work and the funding from Academy of Finland and the European Union. Thanks for attention, and since it's the last section, I put my email here, so if you don't find me around, just please send me an email for possible collaboration. Thank you.
So now the floor is open for questions. We have time for 1 or 2 questions. Let's go ahead. If not, I have one question. We could see from your results that the neurons would align mostly on top of the pillars. Have you checked for the stiffness of the pillars on top and on the laterals?
That is part of this mechanical testing we were not able to show. So the pillars are about 8 megapascal of a young modulus. And we have done this finite element analysis that how much force you apply, how much they bend. Okay. So we have some studies on that ongoing at the moment.
Because what is really interesting is that the cells sit on top.
On top.
Not on laterals.
Yeah, we were very surprised with that. And also for the chondrocytes, they are either in the middle or hanging, but they are never resting on the flat surface. So that was some...
But have you tested to adhere some different proteins on the pillars or not? For example, albumin or some other?
Not yet. It's actually in the plan to make some protein coating of the pillars to see how that affects the attachment points, but we didn't go there yet. Yeah.
Okay. So any other question? If not, let's move on.
Thank you.
The next speaker, and thank you. Let's thank our speaker again.